Okay. Um, Last class, we talked a little bit about the administration of the class. If you got any questions on the administration of the class that were not clear in the syllabus, which is quite possible, then obviously just let me know. We'll figure that out. We then spoke a little bit about two topics. One was just introducing electromagnetic field. So the concepts of electromagnetic fields. There was really a lot of words about electromagnetic fields. And then I did a really quick, a really speedy run through of vector algebra at the end of the class, because I'm assuming that you're comfortable with vector algebra and adding vectors and the products of vectors, specifically the cross product and the dot product, the vector product and the scalar product, because we'll be going to use those in this class a lot. So today's class, we're going to start our work on vector calculus. And this work on vector calculus will cover, I think, including this class, the next 6 classes. So we're going to be spending two weeks on vector calculus. Today's class is going to be specific to differential vector calculus. The next class, Friday, will be an introduction to integral vector calculus. In those 2 classes, we're going to be doing integral and differential vector calculus in rectangular coordinates. And then it's next week that we're going to introduce additional coordinate systems. We're going to introduce cylindrical coordinates. We're going to introduce spherical coordinates. So we're going to expand that sort of toolbox of integral differential vector calculus to make it capable or suitable to solving more problems that have rectangular or cylindrical or spherical symmetries. So that's the basic plan. The point of integral differential vector calculus is that in electromagnetism, we're dealing with electromagnetic fields, which are vector fields, meaning that they exist everywhere throughout space, and at every point in space, there's a vector. That's the vector field. We're also going to be dealing with what we would sort of mathematically call scalar fields. That's again, things that exist everywhere throughout space, but in scalar fields, at each point is just a number associated with that scalar field. And everyday scalar and vector fields are like temperature. There's temperature everywhere in space. That would be a scalar field. There's I don't know, wind velocity everywhere in space. That would be a vector field. And so we're going to work with those, and integral differential vector calculus are the mathematics we use to work with those to be able to quantify, write down what are the sources of electromagnetic fields? How do those electromagnetic fields interact with one another? We do that with integral and differential vector calculus. So that's the purpose of all of this. The first thing I want to introduce is a essential operator for us. The essential vector operator is the del vector operator. And I'm going to write it down in a specific coordinate language, rectangular coordinate, because that's what we're going to be working with today. Or if that is, then it's stupid. So here's the del vector operator. It's given this symbol, which is an upside down triangle with a line over it or a little arrow over it because it's a vector. But this is a symbol's called a NAFA. Here it is explicitly in rectangular coordinates. So if you look in here, it contains the rectangular coordinate unit vectors. So x hat, y hat, z hat. So that's in some sense why we call it a vector. Associated with those unit vectors are partial differentials with respect to the x, y, z coordinates. So partial differentials with respect to x and y and z. So that's what these are. We think of it as a vector operator, meaning that it acts like a vector and it operates on things. When I say it acts like a vector, for what I really mean is it's not a vector that you can draw in space, but it's a quantity that rotates like a vector if you rotate axes. So that's what we mean that it is like a vector. And then it's an operator, meaning that it to be meaningful, it has to have something on there. It has to be something over here on the right-hand side for it to operate on. So we'll always be operating on some function with the del vector operator. Maybe it's a vector function, a vector field. Maybe it's a scalar function, a scalar field. But it's got to act on something to be sensitive. So this is the del vector operator. And we're going to be using that, and we're going to be using its operation on scalar and vector fields. And the operations that I want to introduce are, this is like its scalar product with a vector field. So that's del dot A. A is the vector field. And we call that the divergence, and we often write it just div. So we're going to want to introduce that. We're going to introduce the operation in on that vector field, that the cross product. And this cross product of the del vector operator and a vector field, that's called curl. And these are the two operations that we'll be interested in on vector fields. So just those two things, divergence and curl. And then when we're thinking about scalar fields, we'll be thinking about the operation of del vector operator on a scalar field. I'm writing it just as u here. And we write that operation like this. There's no dot cross product here. This is a scalar field. And this is called the gradient. This is bad whiteboard work to keep crashing into this line every time. So those are the three things that we need for a differential vector calculus right now. We need div, we need grad, and we need curl to be able to operate on scalar fields and vector fields. And what these operations do on scalar fields and vector fields is they explore how those scalar fields and vector fields vary, change. And they explore the sources, the origins of those, and the interactions of those fields. So let's start with divergence. I want to write the divergence in rectangular coordinates. And so let me go ahead and write that down. The way I can write that down, the starting point for writing that down in rectangular coordinates is just to write out this del vector operator in rectangular coordinates, and we're going to write out the vector A in rectangular coordinates, and then we're just going to carry out the dot product. That's all we're going to do here. because I know I will completely overrun the length of the class if I write every equation down in its full glory detail. I'm going to not write every term, but here's the del vector operator in Cartesian coordinates. Here's the first term. And then there's a parallel term for the partial derivative with respect to y, partial derivative with respect to z. And then we've got our field, our vector field. And again, we would write that down in component language. So it has some x component. So here's the x component of the field times the x unit vector, and then there will be again parallel terms for the y component and the z component. So let's just go ahead to get a compact expression for the divergence of a vector field in rectangular coordinates. Let's just go ahead and carry out the cross products. So if you want to think about the cross products that you would have to carry out or evaluate, look, there's three terms in the del, there's three terms in the vector A. There would be 9 possible terms if you multiply these two quantities in parentheses. But, you know, the unit vectors, rectangular unit vectors, are orthonormal unit vectors. We talked about this very rapidly in the last class. Orthonormal meaning that x dot x, that's going to be 1, but an x dot 0, sorry, an x dot y would be 0. So the only of these 9 terms, the only surviving ones that are non-zero, x dot x, y dot y, and z dot z. And the values of x dot x, y dot y, and z dot z are all going to be 1. So we end up with something that's just going to look like ax, the partial differential of ax with respect to x. That's coming from the term I wrote down, and then 2 other terms that arise similarly. The partial differential of the y component of the field with respect to y, the partial component of the z component of the field with respect to z. So this is the divergence in rectangular coordinates. And that's a compact form of it, and that's the form that we'll be using when we evaluate the divergence. The divergence has it's not just a mathematical object, but it really has a real physical significance. Let me just write down what the divergence sort of more physical means. So imagine a little volume, a little infinitesimal volume. The flux of the net flux of the vector field from that volume, the net flux of A from that volume, is this quantity here. It's the divergence times the volume of your little microscopic volume. So you can think of the divergence of A as the flux per unit volume. And then if you multiply it by this little volume element, that is the amount of flux. That would be the amount of field lines that come out of a little region of a charge if we're thinking about electrical fields. So it has a divergence A. Okay, for your mathematician, there's a mathematical property of a vector field, but for physicists, it has a real physical consequence. It's the source of flux of electromagnetic fields. So it measures that. I just want to try and show you that, if I can. I've got to make a sketch to do that. That's the if I can bit, I think. Here's my coordinate axes, and I'm going to make a little cube. on the coordinate axes. Already it's going wrong. This is sort of the out of bounds of the cube. Here it is. So we're imagining this is my little infinitesimal volume that I've created in rectangular coordinates by steps along the rectangular coordinate axis. So that was straightforward for me. What I want to look at is the flux of a vector field, through that surface. So I don't want to draw a whole bunch of field lines, it'll get nasty. But let's just imagine this region of space is bathed in some field that I'm calling a vector field that I'm calling A, and we're going to evaluate the flux. What I think I will evaluate is, or start evaluating, is this cube is made up of 6 faces, right? The top, the bottom, the front, the back, and the left and right. The expressions for evaluating the flux through each face are very similar to one another. And what I'm going to do is evaluate the net flux through this right-hand face and this left-hand face here. And then we're just going to generalize that result to, well, it'll be the same sort of thing for the top, bottom faces, and it'll be the same sort of thing for the front, back faces. These are 2 faces that are, the faces are perpendicular to the x direction, but actually the little area vectors that would represent these faces are either along the x direction because they're perpendicular to the surface, or they're opposite the x direction, again because they're perpendicular to the surface. And the convention is here that surface elements, when you've got a closed surface, the surface elements point out at the surface. So that's the convention I'm following here. So we can imagine we've got these 2 little surfaces on the left and right, and I want to evaluate the net flux through those 2 surfaces. So that's my goal here. So I'm going to start evaluating that over here. I'm just going to call it it's the net flux through the 2 surfaces that are perpendicular to the x direction. And it's going to be made up of 2 contributions. There's the field, flux is field times area. So there'll be a term like this, field times area, for the flux of the field through the surface on the left, and then there'll be another term, maybe I just call this A prime, because it could be different over on the right-hand side, through the right-hand side surface that I'm calling BA2. So that's kind of a symbolic, that's just using the definition of flux and how it's related to field and the area that you're considering. I want to fill it in though in rectangular coordinates. So that's really my big plan here, is to fill this in rectangular coordinates. Let me just write that out. So this is me writing this expression out, symbolic expression out, for the net flux through these 2 faces in rectangular coordinates. So what am I doing in here? One thing I'm doing is I'm replacing the dAs with dy, dz. These faces are made by steps in y vertically and z out of the board. So I'm making them with those 2 steps, and their areas are dy, dz. So I've done that. I've done it here, and I've done it over here. I've also done another thing. The area vectors One points towards the right, the positive x direction, and one points towards the left, the negative x direction. So this plus sign and this minus sign are reflecting that the two surfaces are pointing in the opposite direction because they're on opposite faces of the cube. So that's where the signs come from. And then finally, I've said, well, look, what counts for flux is through a surface is the perpendicular component of the field through that surface. That is, it's the field that's parallel to these surface vectors. So it's not A as a whole that contributes, it's AX that contributes, the X component. So I call the X component AX over here on the left. It could be a little bit different over here on the right? The field could change. And so I called that AX plus DAX. That's why I use the prime and no prime upstairs here. So this is my expression. I could compress this, right? There's a lot of cancellation out that goes on here. The first term with a chunk of the second term, all that survives is DAX times the area of dy dz. So that's what survives, i.e. the net flux through those two faces would be zero if the field didn't change. The field's got to get stronger or weaker in the x direction for there to be a flux. I could actually write that in a way that's going to help us. I'm going to divide, we've got two little line elements here. There's one more, dx. I'm going to divide through by that for the field term. But that means I've got to put a dz up here, dx up here for the this term. And then I've got a dy, dz, dx. That becomes the little volume element. So this is a volume element, dv. Okay, so I just put a dx in the denominator and a dx in the numerator, so I'm not doing anything. And then I'm identifying this as a, I really want to identify this as a partial differential of the, and I got this from x component of the field with respect to x times this volume, right? So this is a compact expression for the x component of the field's contribution to the net flux through this cube. The other pairs of faces, the front and the back, the top and the bottom, will create equivalent contributions. It's just instead of the x component of the field being important, it'll be the y component or the z component. So if I want phi, I've just got to, well, if I want the total phi, so this is the flux through the x and y and z pairs of faces. I've got this contribution, but I'm also going to have the contribution from the top and bottom and the left and right. I can put those all in. This is the one that we computed, but there'll be a contribution that looks like this, how the y component changes in the y direction, how the z component changes in the z direction. And that all becomes the volume element. And if you look at this equation here, this is nothing other, this equation that I've written down is nothing other than del dot A, the divergence of A, times the little volume element of our volume. This thing in parentheses that we constructed is, if you look over there on the right-hand side of the board, left-hand side of the board, it is the divergence of A. And so it tells us what the divergence means, this little exercise. This is the flux emerging from some microscopic infinitesimal volume. So this whole thing is a flux. So the divergence itself is kind of like a flux per unit volume. That's the meaning of it. And so not only is it a useful mathematical quantity, but it has a physical meaning. It's measuring the number of field lines that are emerging from that volume. Okay. Anyway, that's divergence. Divergence, just to summarize, it's a scalar product. So it's going to create a scalar quantity. There's no unit vectors here. This is just a scalar quantity, a function or a number. And it's simply just the sum of the partial differentials of the field, of each component of the field, with respect to each component's coordinate. Okay, we've got to do the same thing for curl. And so let's go ahead and do that. So we want the curl of a vector field, cross product of del and the vector field A. We want to write that down in rectangular coordinates. The way to do this is exactly the same as the way that we did the divergence. So we're just going to take this kind of general symbolic representation of the curl of the vector field, and we're going to express the del vector operator, and we're going to express the vector field now in rectangular coordinates. So actually, just write out a couple of terms in that. The del vector operator, we've got it written up here. Here's the first term, and then there's parallel terms for partial differentials with respect to y and partial differentials with respect to z. So something like this. We're going to then take the cross product of that with the vector field itself, which again, I'm not going to write down every term, has a vector field in general has three components. We can write it in terms of the unit vectors of rectangular coordinates as the x component times the x unit vector, the y component times the y unit vector, the z component times the z unit vector. And we're imagining that I took the time to do that. When we evaluated the divergence, we did it by just saying, well, look, in this product here, we've got in parentheses on the left 3 unit vectors, parentheses on the right 3 unit vectors. There's 9 possible products of those 3 terms in the 2 groups of parentheses. And we evaluated all of them using the nature of rectangular coordinate unit vectors. Exactly the same here. Exactly the same here, except we're doing a cross product rather than dot product. So what would that mean? When we did the dot product, x dot x was 1, y dot y was 1, z dot z was 1. All the others were 0, and so only 3 terms survived when we evaluated the dot products. The reverse is true for the cross product. If you have x cross x, well, cross product is evaluating perpendicularness. X cross x is 2 parallel vectors, so x cross x is 0. So those die off. X cross x, y cross y, z cross z are going to die off. The survivors are like the x cross y, which are two perpendicular vectors, which give the third direction, give the z direction. And so instead of three surviving, the parallel unit vectors and the six perpendicular ones disappearing, now we've got six surviving, the perpendicular pairs of unit vectors, and the ones that die off are when you've got x cross x and y cross y, etc. So we're going to see six terms. And I'm going to write down these six terms come in three pairs associated with the three different unit vectors. So here's the first pair of partial differentials associated with the x unit vector. These come about when like z cross y is minus x and y cross z is x. So those combinations, that's why one has a plus sign and one has a minus sign, because when you do it in sort of clock order, y cross z is x, but when you do it z cross y, that's minus x. So that's the first term. And then there's corresponding terms for involving the y unit vector, this would be a bit more explicit, and the z unit vector. These corresponding terms have, again, a pair of partial differentials multiplying the unit vectors in each case. You'll notice that the partial differentials involve the two components of the field that are not the unit vector that they're multiplying. And the partial differentials themselves involve the two coordinates that are not the unit vector that they're multiplying. So that's the kind of pattern here. So if I was to write down the term in y, it would involve the partial differentials with respect to x and z, not y, of the field components ax and az, not ay. Same idea over here. Okay, so that's just carrying out the cross products. There's a very convenient way of writing this. And it's as a determinant of a matrix. It's a determinant of a 3 by 3 matrix that has a kind of simple structure to it. And the simple structure is the following. Across the top row are the unit vectors, as cylindrical coordinate unit vectors. Across the middle row are the partial derivatives. So these are the terms in the del vector operator. And across the bottom row are the field components. So that's easy to remember. If you think about evaluating the determinant, what happens when you evaluate the determinant? I'm not going to go through every step of it, but we'd start here. And this term up here, the x unit vector, would be multiplied by the difference between this product, which is the partial differential of the az with respect to y, less this guy here. So we multiply by plus this, and we subtract and minus this guy here. This is day by dz. And that's exactly the term we got up here. And so this is just a different way of writing it, but it's a very handy way of writing it, remembering it, not getting jumbled up in all these different partial differentials. So it's very neat and very handy for us. We said in the case of the divergence that it kind of had this physical significance as the flux per unit volume. that was originating from some tiny volume element. The same is true here, but not the same, but a similar thing is true here. This quantity, the curl of A, not that quantity, the dot product of the curl of A with a little area element. So when we were talking about divergence, it was the divergence of A multiplied by volume element. But now it's the curl of A, dot product with a area element. It's a dot product because both these are vectors, right? If you have a little area, that's a vector. It has a size and it has an orientation perpendicular to the vector. And this curl of A is a vector, right? The cross product of two vectors is another vector. This quantity is the circulation of a field. That's kind of the rotation of the field. So the rotation of the field A around dA. dA is the little area element that we're thinking of. Is the circumference of it is like a little loop, and this quantity here is the amount of rotation that's generated within that little loop, by the surface within that loop. Just like for the divergence, the divergence times dV is the amount of flux that was generated by that little volume that we'd enclosed. This is the amount of rotation or circulation that's generated by this little loop this little area that we've enclosed with a loop. So this also has a real physical significance, not just a mathematical significance. Okay. I proved for you the physical significance of the divergence of A. I just quoted for you the physical significance of the curl of A. But it's the same sort of proof. In the divergence of A significance, we imagined the little volume, dx, dy, dz, and calculated the flux that was emerging from it in rectangular coordinates. Here you would imagine a little circle, maybe with dx and dy or dx of dt or dy and dz, and you calculate the flux, the circulation, the rotation of the field around that loop, and you would come up with this interpretation. So it's essentially the same proof, the same method to prove it. Those are the two things that we need for vector fields in differential calculus. So we've done all that. That's good. We've got one more thing to do, which is the scalar field and the gradient of the scalar field. That's the other bit of differential calculus that I need to introduce. And so let me go ahead and do that. And again, my starting point, we started out by writing div A in rectangular coordinates and then curl A in rectangular coordinates. I'm going to write the gradient of U, the scalar field, in rectangular coordinates. And so let me just write that out. We often call this grad U. So that's kind of how we might say it, the gradient of U. To figure an expression for it, what did we do before? We wrote out the vectors in rectangular coordinates. We've only got one vector here, and then we've got a scalar potential. So I'm just going to write out x times the partial derivative with respect to x plus corresponding terms for y, the partial derivative with respect to y, plus the z unit vector and the derivative with respect to z. So those three terms as usual. And here's the function u, the scalar function u. There's no ux's or uy's or uz's. It's just the scalar function. Any point it has just a value, single value. So let's carry out this product. This is easy, right? We've just got to multiply each of these, sort of multiply, or let this operator act on each of these scalar potentials. So this result is this guy here. It's a vector quantity. That's an important thing. We just made a vector out of a scalar potential and the del vector operator. So it is a vector quantity. You can see that because I've got these unit vectors here. And the terms for each of the unit vectors just involve the partial derivatives of the scalar potential with respect to the x, y, z coordinates. There's just this little expression here. This also has a physical significance. And I'm going to write that down. Not just the mathematical significance of the gradient of the scalar field, but rather this product here of the gradient vector and a little line element vector, that's the ds. That product, that dot product, these both vectors, right? The gradient is a vector and the line element, that's just a step in space, that's a vector too. So we need either a dot or a cross product. This dot product is the is change in u or this little incremental step ds. And that physical result, the gradient of u kind of reflects how much the scalar field is changing. And then if you multiply by the step you're taking, that is the change, parallels what we found for the curl, which reflects the circulation or the rotation that was generated by a certain location in space for the vector field, and the divergence, which was reflecting the source of flux of the vector field at a particular location in space. So each of these things ends up having real physical significance. So I wanted to summarize, and I think I'll summarize by just showing one slide. So normally I'm going to work, well, first class I worked off the slides, although not entirely successfully worked off the slides. In this class, I've essentially worked off the whiteboard. I was just going to show you one summary slide. I might try working off the document camera, where I could record much clearer than on a whiteboard in the video what I write. And so I think I'm going to try that too. And then you can let me know. I mean, do you hate the document camera or the whiteboard or the slide? You can let me know your preferences. But this was the summary slide. All this works perfectly today. Now we're beyond the first day of class. This is what we did today. We introduced del vector operator. Remember, we said it was a vector because it kind of rotates like a vector. It's an operator because it needs to act on something to be mean. Or a vector field, do have a little vector over this here. We defined, using del vector operator, its divergence and its curl. These are the two properties that are important, mathematically important for describing a vector field. The divergence of the vector field is a scalar quantity that's the sum of the partial differentials of the field with respect to the X, Y, Z coordinates. The curl of the field, we also describe that. The curl of the field is a vector quantity, so it has a size and a direction. The divergence only has a size. And a compact way of writing it is in terms of the determinant of this 3x3 matrix involving the unit vectors, the del vector partial derivatives, and the fields components. And then we said that we also need to describe the changes in a scalar field. We call the scalar field U. There's one change that's important for us. It's the gradient of U. That's a vector too. It's like a vector. You just think of these things as multiplications, right? Dot product's going to make a scalar. Cross product's going to make a vector. Scalar times a vector is going to be another vector. And here's that vector. That vector just involves in rectangular coordinates the partial differentials of the field with respect to each of the scalar field with respect to each of the rectangular coordinates times the rectangular coordinate unit vectors. So this is a kind of math of differential vector calculus. Over here on the right-hand side, I've tried to summarize the physics that lives in this calculus. And we said that the divergence of the vector field, that's kind of a flux per unit volume, measures the flux per unit volume at a certain point in space. If you multiply by the volume of that little point in space, that will give you the net flux emerging from that location. Similarly for the curl, this symbol here is a symbol that sometimes the gamma used for circulation or rotation. So you can think of it, the curl as measuring source of circulation or rotation at a particular point in space. It's kind of the circulation or rotation per unit area. If I multiply it by an area element, it tells me how much circulation or rotation that little area element is contributing. And then finally downstairs here, this is the third physical significance. If you've got a scalar field, what's the important thing? How it changes when you step from one location to another location. The gradient of U is kind of measuring the slope and the direction of the slope of the scalar field's change, such that the change in U, if you take a step ds, is given by this little expression here. So you see these physical meanings kind of parallel each other, going from volume elements to surface elements to line elements as we walk from fluxes to rotations to changes, and involving the Darwin cross products with the vector field and the this single product of the del vector operator and the scalar field. I think I'm going to end there. Any questions on all that? The next class is to talk a little bit about integral vector calculus, and most specifically line integrals and surface integrals at the beginning of the class. Then I'm going to move on to some illustrations, some examples. And really there's no illustrations examples today. So Friday will be some illustrations and examples, and Monday, following Monday, will be illustrations and examples. Okay, thank you.